So it is my pleasure to introduce Rainer Mandel from KITE, so Karlsruhe Institute for Technology, and he will speak about dual Nonlinear equation and polychromatic solution of nonlinear wave equations. So,
thank you, Jean-Baptiste, and thank you, Hugo, for organizing this seminar. It's a pleasure to be here, to be virtually in the seminar. So let me briefly tell you what I want to do today. So in the first section, I want to talk about the dual variational method, and I would like to describe the main idea behind and to describe the principle and why it is useful in the problems, in the mathematical problems that I'm interested in. In the second part of my talk, I would like to concern one generalization of what one typically calls dual variational method, namely I want to apply it to the nonlinear Helmholtz equation with sign-changing nonlinearity, and we will see that the dual variational method there becomes more difficult because of strong indefiniteness of functionals. In the third section, which is completely disjoint from the second one, so it's really another topic, we consider another variant of the dual variational method. We apply this to produce solutions, so polychromatic solutions to the nonlinear wave equations with power type nonlinearities. And in these two areas, this dual variational method applies, and that's why I start with explaining it at the beginning. So before telling you about the dual variational method, I have to say something about the variational method in general. So consider the following toy example. When you have a simulated elliptic PDE that you're interested in, for instance, this one on top here, which is labeled 1. So minus Laplace and u plus lambda u is equal to u cube. And typically you consider this in an open domain in R3, say, with homogeneous boundary conditions. And this problem has a variational structure, which is well known. So it has an Euler functional I defined on the Sobolev space H01. And it is given by this formula that you can see here. The first part here of the functional here generates the left-hand side of the equation. The second part generates the right-hand side of the equation. And the boundary condition is contained in the choice of your space. And a nonlinear version of Dirichlet's principle tells you, okay, if you want to solve this equation 1, you just have to find a critical point of your functional I. And actually, the same way it goes the other way around. Here, I did not make precise what a solution means. Typically, one is interested in weak solutions or classical solutions. If omega is regular enough, so if the boundary of omega is smooth, then all these notions coincide. So there should not be any problem with that matter. So I just recall here, this Sobolev space here is the closure of the test function with respect to this norm. Here you can add the EL2 norm or not, which is a consequence of Poincaré's inequality. So that's variational methods. How can they be used in such an example? If you have a look at it, then you could be tempted to find minimizers or maximizers. This is not a good idea, because the function is unbounded from above and from below. So none of them exists, and the only local minimizer which is easy to find is the trivial solution. So there is not much hope to find any minimizer or maximizer. On the other hand, there are variational techniques that provide saddle points of such functionals. Say, for example, the mountain pass theorem that applies for lambda bigger than minus lambda 1, where lambda 1 is the first Dirichlet eigenvalue. And this result is due to Amposetti and Rabinowitz from 1973. The linking theorem gives you even a result even when lambda is below that value, is contained strictly between strictly contained between two eigenvalues, then, so to say, you have a quadratic part here which has a finite dimensional non-degeneracy. And for such problems, you still have good tools, like the linking theorem. And the question is now, what can you do when the situation is a bit different? So you have omega in R is equal to R3, which is the typical case for a Helmholtz equation, or it could also be an exterior domain. And you have lambda smaller than 0. In that situation, you have two or multiple problems actually. So one problem comes from the fact that your space is unbounded. You have problems with ensuring compactness. You have translation invariance in your problem. So what can you do? And the next problem is, and which is actually more fundamental, I would say, is that when lambda is smaller than 0, then minus lambda is actually in the spectrum of the Laplacian. And that means that here you have a big trouble to control this this term here in the definition of your function. So it's not even like that you cannot find a critical point theorem in the literature which could work for the Helmholtz case. It is even, or it should be even, impossible. I say should because if we add some extra conditions, then one can make this rigorous, because one knows that Helmholtz solutions of the Helmholtz equation, so solutions of minus Laplacian minus lambda u equals some right-hand side, that such solutions cannot be in L2. So there's no hope actually to find solutions using a critical point theory, at least not in H1 or in L2. So what can be done? And the answer is you can use dual variational methods, and this was used for the first time in the context of nonlinear Helmholtz equations by Ivico and Witt in 2015. And to explain this a bit further, I will now say a few words about the dual variational method in general. Here's the attempt of a short description of this method. So it's the application of classical variational methods after interchanging the roles of linear and nonlinear terms by some substitutions of variables and inversion of the linear operator. So what does this mean? Just schematically, if you have L u is equal to f of u, you want to solve this equation. So what would be the dual strategy to find solutions? You first apply the inverse, namely L to the minus 1, and then you replace the variable itself, namely you make the substitution f of u is equal to v, and you end up with this problem here on the right-hand side. And if you're lucky, then this problem here has a good variational structure, and you can use a critical point theorem from your list before, so mountain path theorem, for instance, or even different critical point theorems. And in such a way, you can find a solution of this equation. What is the advantage? The advantage is that in this new equation here, you can remove the strong indefiniteness of your linear operator L, if such a one exists. Yeah, and even what is important in the Helmholtz case, you need not have true inverses, but also right inverses are okay. So that means if you do this with L to the minus 1, so when L to the minus 1 represents a right inverse of the operator, so in our case of the Helmholtz operator, then you can study this equation here and produce some critical points, and these critical points will, by inverting this substitution, produce a solution of your original problem. The other way around, it doesn't work because you only have right inverses. But never mind, you can find a solution of this equation here by solving the dual problem, actually. And the disadvantage is that f needs to be invertible. So typically, if you have a power type nonlinearity, then you require the coefficient in front to be positive or even negative, but sign changing is not possible. And that's the point that I would like to comment on later. Let me now say a few words how this method can be applied. So I think the first, or one of the first occurrence of this strategy was in 1980 when Précis-Coran and Nienberg applied this method to the nonlinear wave equation that you can see here. So they considered the 1+1 wave equation with a p-1 power nonlinearity on the interval from 0 to pi with homogeneous boundary conditions, and they looked for time periodic solutions. And they used a kind of right inverse, that's what I call here K. So in this paper, it is also called K, that allows to rewrite this equation here in this setting, in this way. And now if you choose a good space X, and if you make the various substitution that turns your u to the p-1 into v, then you end up with this equation, which turns out to be variational. And Précis-Coran and Nienberg used this kind of strategy to prove the existence of a non-trivial bounded solution with the aid of the mountain pass theorem now in this dual formulation. This was pushed further in 1992. This dual method was used by Alama and Lee in the context of Schrödinger equations on the full space. And here, the main feature of their problem is that this lambda here is not small, but can be large in the sense that lambda can be really in some spectral gap of this operator. So it's not necessarily below the spectrum, but in a spectral gap. And in this case, you have a strongly indefinite linear operator that can be removed by using this dual strategy. And that's precisely what they did. They started from this equation here, applied the inverse operator, performed this variable substitution, and obtained an equation that they could discuss with variational means in LP prime. And again, using the mountain pass theorem, they concluded that this equation here has a non-trivial solution. Here, I emphasize once more that the positivity was needed. So formally speaking, this is needed in order to make this substitution, because here you see some power. But okay, even this could be circumvented, but let me put it like that. This positivity ensures that you have a definite term here in front. And we will see that in the sign changing case, this will be different. But before I come to that, let me finally mention the application of Evico and Witt in 2015. They were interested in this nonlinear Helmholtz equation. And now the strategy is to apply the right inverse of the Helmholtz operator, RK. I will say a word about that in a second. And following the same strategy as before, perform the variable substitution. And this variable substitution makes sure that you have a variational structure in V, and you can define your energy functional for this equation here and obtain the existence of critical points. Let me mention that Evico and Witt even obtain infinitely many solutions under these conditions because they could apply the symmetric mountain pass theorem, because we have an even functional here. So this helps in obtaining infinitely many solutions. Okay, they have further results, and there are further results in the literature. Also some results for Q periodic, for instance. But still, the dual variational method is somehow limited to the case of positive Q, and that's what I want to discuss in the next section.
May I ask you something? Sorry.
Yeah.
Interrupt. So where is this lower bound on P coming from?
Yeah, that's what I'm going to explain on the next slide.
Okay.
So it's okay. The upper bound is clear. This is from Sobolev embedding. The lower bound is the so-called Stein-Thomas theorem, Stein-Thomas exponent. So it has to do with Fourier restriction theory for on spheres. Let me explain this on the next slide. So what is the reason for this restriction on P? So there's this theorem by Koenig, Ruiz, and Sorge from 1987, where they proved that this right inverse RK, obtained by a so-called limiting absorption principle, that this operator is bounded precisely for P in that range. So as I told you before, this is due to the, say, Sobolev criticality. Has to do with the fact that the symbol of the Laplacian here goes like xi squared as xi tends to infinity, and this exponent here comes from the fact that we have a singularity here in the construction. Let me explain this. So in order to construct such a right inverse of the Helmholtz operator, what you do is you shift your spectral parameter into the resolvent set so that you can have a good resolvent. So classical resolvent from L2 to L2. And then you let this approximation go to 0. So you go back to the original problem that you're interested in, and you want to save as much mapping properties of this operator as possible. And this is what so a good limiting absorption principle gives you good topologies in which this limit here exists. And Koenig, Ruiz, and Sorge were able to show that this operator is a well-defined operator from LP prime to LP. Yeah. It has, as I just said, the Stein-Thomas exponent comes into the game, because here this symbol becomes singular at a sphere, and Fourier restriction to the sphere is governed by this Stein-Thomas inequality. To explain this would require maybe another talk, but only very roughly. If you want, I can try to give more details later on. One can also give an alternative description of this operator in terms of a convolution operator, which is oscillatory. So here you have some definition in terms of Bessel functions, which in the case n is equal to 3 simplifies to such an expression. So you have an oscillatory behavior of your kernel, and you have a weak decay rate. That's somehow the challenges that you have to deal with in the context of Helmholtz equations. Okay, so this operator was used in the dual variational method. Let me also mention a theorem with Montefusco and Benedetta-Pelacci, who is online. We generalized this in the sense that we could also apply this to negative potentials. So we have basically the same result as Evico and Ved for positive potentials, but also for negative potentials, because both functionals here have this mountain pass geometry. And so the question is, what are the common features? Can we do also the case in between? Can we do this for sign changing Q? And that's now the point where I go to the second part of my presentation, where I want to talk about our recent results in this direction. So we are interested in a dual variational method for power type nonlinearities in the nonlinear Helmholtz equation, where the coefficient changes sign. So this is not yet a preprint. It's really in press, so to say. It's a collaboration with Dominik Scheider, Tobias Witt, and Tolga Ježel from Frankfurt. as I mentioned, we're interested in this problem here, where Q is sign changing. And actually, we have to modify the problem to be able to treat this. If we consider this problem here, then we can write Q as Q plus minus Q minus. So the positive part minus the negative part. And instead of that, we introduce artificially some parameter lambda. At the moment, we need that, unfortunately. Yeah, but this is really artificial and due to our method, I think. So what can we prove in such a situation? We have the same assumptions mainly as before, and assume that Q plus is not identically 0, and that the diameter of the negativity set of Q is smaller than some constant divided by K. So if we take K is equal to 1 for the moment, we can only say, okay, there's some number only depending on the space dimension, such that this inequality should hold. This is an explicit number. It's the first zero of some Bessel function, basically the Bessel function that you just saw on the previous slides. So it's controllable. It's not a perturbative statement. Okay, under this assumption, what can we say? Then for almost all lambda bigger than lambda 0, there's a non-trivial strong solution of this equation here. So to summarize, we want to have that Q minus, that the effect of our negative component that the negative part of our coefficient only is concentrated on some sufficiently small ball, and once we have guaranteed that, we can produce solutions. Yeah, I have to explain a few things. C0, I already mentioned what this is, but why almost all, and what is this lambda 0 here? This I want to explain in the following. So what is the strategy? I want to use the dual variational method to find solutions. The idea is to use 2 variables instead of 1. So previously there was this mapping which goes from U onto V, and now we introduce 2 variables that take the behavior on the positivity set of Q into account and on the negativity set. So we introduce 2 independent variables, and this phi variable is concentrated on the positivity set and psi on the negativity set of Q. And so they both carry, so to say, the information about U, and allow to write down a dual variational formulation for the problem. So what we will end up with, and this is what I'm going to explain on the next slide, if we do this this substitution, then we obtain a strongly indefinite dual energy functional. What can we do with that? Under these assumptions, which I just mentioned, we can use the saddle point reduction with respect to psi to obtain a good functional, for which we can use the mountain pass theorem, or say a variant of it, which is due to Jean-Jean and Toland. And once we have found a critical point of J in that way, we know that these critical points have infinite Morse index, in the sense that there's an infinite dimensional subspace in which, with respect to which we have to have maximized. Yeah? So in an infinite dimensional space that points downwards, so to say. So that's the effect. That's the effect of sign changing nonlinearities, that you have infinite Morse index solutions. Okay, to be a bit more precise, So we have this variable substitution, and let me show you that this gives rise to a new variational problem. So we are starting with this equation. We want to use this definition. So the first thing is to replace the right-hand side, and the definition is made in such a way that, that we can write it like that. And taking into account that phi, by definition, has only support in the positivity set and psi only in the negativity set, we can even write it in that way. So we have here the modulus, and instead of solving this problem, we use the dual, we solve the dual one, where we use the right inverse RK. So there's no implication in that direction, only in the other direction, because we have a right inverse. Okay, so now we want to solve that, and now we have to reformulate the left-hand side here in terms of phi and psi to obtain an equation that we can solve with the calculus of variations. So what do? We split this up. So, this is now an equation on the positivity set, and this is an equation on the negativity set. And this can be simplified even further. Now, with this strange prefactor here in front, we can write it like that. And this is the Euler-Lagrange function. This is the Euler-Lagrange equation of a function, namely of this one. So this is the dual energy functional that we get, and it is defined on LP prime of the positivity set of Q and LP prime on the negativity set. And here we have the strong indefiniteness becomes apparent. Okay, we also see that in the case when we are only positive, so when A minus is when A minus vanishes, then we can simply cancel every psi from this formula, and we recover the functional that was introduced by Ewig und Witt. So it's a true generalization of this approach. Here, what is this K? K is this operator that you can find here on the previous slide, this one here. Our assumption on Q, namely that Q vanishes at infinity and belongs to L infinity, makes sure that this operator K is compact. And this helps actually to deal with this strongly indefinite functional. As I said before, what can we do with this functional? If you look at this functional for a couple of hours or days or weeks, as we did, then you realize that it could be a good approach to use maximization with respect to psi and the mountain pass theorem afterwards with respect to phi. And let me briefly explain how this works. So you fix phi first and you consider maximization. Maximization with respect to psi, and the relevant part of the functional is given here. This is a good one for maximization. This is not a bad one, at least, because psi is only linear, so this is okay. But this one could produce trouble if it was if it pointed in the wrong direction. So if psi k psi is non-negative, then everything is fine, and that's what we use as an assumption. We wanted to have that this term here is always non-negative, and this can be ensured by choosing this negativity set of small diameter. This is the reason why we consider small diameters for the negativity set, because only under this assumption we can guarantee that this part here is non-negative, and so that it makes perfect sense to consider maximizing sequences and to prove their boundedness and later on their convergence. So this is used here. Why is there a diameter condition? This was found by Jan Ewig und Witt 1 year ago. Just very roughly, if psi has a small diameter, then you can write this as a convolution, and both again this psi tilde has small diameter. Have small support, so that you can actually reduce your convolution to that region here. And this has the advantage that when you now use the Plancheret theorem, then you have a different function here, and you can check that it has non-negative Fourier transform. This is a non-trivial fact. So the computations related to that are at least 2 pages or 3. So we are happy to have found this result, and actually it is Tobias Weth who pointed that out to us. Okay, so non-negativity of this part here ensures that we have a good structure for maximization. We consider maximizing sequences and prove their convergence by using the compactness of K. So this is not a problem. So you have now a maximizer that's summarized here in this proposition, which depends continuously on your phi. And it's uniquely determined because we have a strongly concave function. We have a norm estimate for it, and we can even conclude that this reduced functional here is C1. This is now the point where you can see, okay, now J lambda tilde, this reduced functional should be the one to which we apply the mountain pass theorem, because it turns out it has the right structure. I don't want to verify this structure here in detail because it's would be another set of slides, which might be too complicated. So I just want to tell you that this has the mountain pass geometry for special data. So we define alpha, beta, and lambda 0 in that way. Yeah, just accept it. There's some lambda 0 that we can define in dependence of our Biermann-Schwinger operator, and hence independence of the coefficient function. And then one can check that for lambda bigger than this threshold value, this sequence here of this family of functionals has the uniform mountain pass geometry, and that this monotonicity condition is also satisfied. This monotonicity condition is crucial for obtaining bounded Palismay sequences, because in our we would like to apply the mountain pass theorem, but when we try to do it, we always failed because we were not able to prove the boundedness of Palismay sequences. And so the idea was to take this result by Jean-Jean and Toland, where the monotonicity trick is presented, and they provide a good criterion that ensures the existence of bounded Palismay sequences for almost all lambda. So here, not for all. And so this seems to be crucial, at least because we want to use this result. Yeah, once we have such a bounded Palismay sequence, the rest is rather easy because we have a compact operator K here. And once we have established the boundedness, we get the existence of a critical point quasi gratis. And yeah, that's the way we prove the existence of a critical point. So let me summarize. We pass through the dual formulation. We have a strongly indefinite problem. We maximize with respect to one variable, and we take the mountain pass with respect to the other, and then using this Jean-Jean Toland result, we can prove the existence of a critical point. So open problems related to that. Is there any alternative for this condition? Can we deal with bigger negativity sets of Q? Are there variants of this result where Q does not vanish at infinity? Because now our approach relies pretty much on the compactness of K. This might be not needed. then it is unclear from our presentation, from this in particular, from this presentation where I did not give any details in this direction. But yeah, is our lambda 0, is this optimal? And of course, almost all is a bit disappointing. It's something, it's more than nothing, but it appears strange to me. So the question is, do really all lambda bigger than 0, bigger than lambda 0 apply? This could be for solved, for instance, if there were a priori bounds for solutions, but unclear how this should work. And finally, is there a general variational principle or a general variational framework in which we can put our assumptions? Because we only carried out this out for the nonlinear Helmholtz equation, but I think it could be useful also in more general contexts. Okay, what you should keep in mind from this from these slides is that when you have a sign changing right-hand side in your elliptic problem, then once you pass to the dual variational formulation, you get an indefinite problem. And actually, there's also the arrow back. But anyway, that should be the summary, maybe, of this second part of my presentation. Yeah, and I would like to go on with a completely different topic, say, or now it's about nonlinear wave equations. But it's actually not so disjoint because we use the same operators again, but it seems to be different. I would like to start with a definition of a breather solution. So which will be polychromatic solutions of nonlinear wave equations. So here it is said in Wikipedia, in physics, a breather is a nonlinear wave in which energy concentrates in a localized and oscillatory fashion. So for us, this means consider a nonlinear equation and try to find space localization and oscillatory behavior with respect to time. In our case, this will be time periodicity, which will be required. So such breather solutions can be found in the literature. Not many of them, by the way. As solutions of the nonlinear Schrödinger equation or Korteweg-de Vries equation, nonlinear wave equations, and such things. Boussinesq equations, so fluid dynamics also plays a role, I think. What I'm interested in is the topic of real valued polychromatic breathers. So I don't want to just plug in a standing wave ansatz and obtain a localized solution. This would be too easy. That's not what I want. I'm interested in real valued solutions. So the prototypical example here is the sine-Gordon breather, which has the advantage and the charming feature that it is explicit. So here you have the corresponding formula. You see it is time periodic. This is due to the sign here. And the strong localization in space can be seen from this this hyperbolic cosine. So this is up and down, up and down, up and down with respect to time. And if you follow the video, then you can guess why it's called a breather, because really it's a kind of breathing mechanism. It's like so up and down, and that's why it's called a breather. So that's a rather famous and interesting one for the sine-Gordon equation. There are various other types of explicit families, which I don't find so very interesting, I must admit. What is more interesting for me is a result by Planck, Kyrillos, Bruckner, Löscarré, and Schneider from 2011. They used a very special one periodic step function V. They considered this wave equation again in a dimension 1 + 1, and they proved that there is a a breather solution which has this strange period, which is strongly localized in space, and is small. So there can be breather solutions of that kind. So real valued. This the point here. So it's not a standing wave. It's so not standing wave in the sense e to the I omega t u of x, and that's it. No, it's a much more sophisticated construction, and these methods are completely disjoint from what I'm able to understand or what I'm doing. So also the 32/13, yeah, it's a bit strange, and this periodic step function is also very, very fine-tuned, say. So everything breaks down if you consider little perturbations of it. And so the question is whether this can be generalized. Let me give another example by Wolfgang Reichel and Andreas Hirsch in 2019. They considered a similar problem here, and they considered also strange potentials. So periodic step functions, periodic delta distributions, and rough perturbations of the constant. What does this mean? You need a certain amount of roughness, that means discontinuity, so that sufficiently large gaps in the spectral theory of the corresponding Hill operator or Schrödinger operator open. This is somehow behind. It is known that if you have a smooth potential, then these gaps of your negative Laplace of your Schrödinger operator, they become smaller and smaller, and only if you allow for very rough potentials, you can ensure that your spectral gaps are open, so that infinitely many modes actually fall into spectral gaps and allow to prove the existence of localized solutions. I know this is maybe this was not very helpful, but maybe we will see in a second what this means. Because the ansatz is a polychromatic ansatz as a Fourier series, and then it becomes more clear. So they proved that for a certain periodicity and sufficiently small tau and p bigger than 0, we have breather solutions. And what we were able to do with Dominik Scheider is to prove the existence of breather solutions for wave equations, for nonlinear wave equations. Now, without any rough potentials, but the main feature is now that we are on R3. So the higher dimensional case, which seems to be completely different. And we are not seeking for L2 solutions, but for solutions that have a weaker decay with respect to space. So our result, for instance, says, so if Q is positive and sufficiently localized, and the exponent here is not too big, and your exponent Q is chosen in a reasonable way, then we can find the existence of an unbounded sequence of distributional breather solutions. So here, this has many features which the previous results do not have. And let me comment on a few, but before, let me say there's also a more general version of it in arbitrary space dimensions. Again, you have this Stein-Thomas exponent, as we saw before. And again, under these more general conditions, we can prove the existence of breather solutions. So here I recall what a distributional breather should satisfy. The new features now to the theory are we use a variational approach, where in the higher dimensional case, we can treat general P. This is actually also the case in Wolfgang's result. Then we have large breathers, not only small ones. This is all also in Wolfgang's approach, I think. So we have a weak localization. This is now a rather bad thing, I would say, because typically physicists are interested in strongly localized functions, but ours are only localized in a weak sense. This is the bad point of our result, but we have real valuedness, which tells us that we have not a standing wave. And we also have a polychromatic state, because we can check simply by plugging in this ansatz that such such solutions are not found by this method. Okay, and this also has the advantage of admitting generalizations, which are so the framework is not so strict as in the previous results. What is the idea? The idea is to come up with this ansatz here, which ensures that U is real valued and polychromatic, actually. Yeah. So you use this Fourier decomposition. Then you derive from this an infinite system of coupled nonlinear Helmholtz equations. So for each mode, so for each of these UK, you get a nonlinear Helmholtz equation. This one you solve again by some inversion of the linear operator. So here you see this is the dual variational method which comes into the game. You perform some variable substitution, which is essentially the same as before. And then you see you have a variational structure for this function v, and you apply the symmetric mountain path theorem and obtain critical points and as a consequence solutions of your of the problem. So the strategy is again a dual variational one. So the main difference now is that we do not consider one mode, but infinitely many of those. This is the main thing here. So what we need is the Hausdorff-Young inequality. So we can write a function in terms of its modes. So these modes will be written that way. And in the following, we will use the Hausdorff-Young inequality. I won't check this in my computations now, but just for you as a hint, what tools do I need here? Hausdorff-Young inequality is one of such tools, and again, I need this operator RK from before, this Helmholtz right inverse, because this one allows to solve Helmholtz equations as I explained before, namely, given a right-hand side f, a solution of this Helmholtz equation can be found by putting U to be equal RKF. What we need is that in suitable spaces, this operator RK is bounded and even sometimes compact. So here the same tools, the same result by Ruiz, Sogge, and Koenig. So this is based on the same result as before. So how can this dual variational setting be implemented? We want to plug in this ansatz. And what we end up with is that if we plug in this ansatz, then we get an equation for the kth mode, namely that the kth mode should satisfy some Helmholtz equation, where the right-hand side is the kth mode of this nonlinearity. So formally, this means this one here.
But this is a system with infinitely many equations, right?
Yeah, this is for all k belonging to this index set. Mm-hmm. For all k, we have to solve this simultaneously. Here we split this Q in a somehow artificial fashion, but this is rather the same idea as before. From this one, we get that instead of this one, we should solve this equation here. So here we are performing the dual variational approach. So first invert the linear operator and make this variable substitution. So this is what we do here. And now we have to replace UK in terms of the V. This can be done using this formula here, summing all the modes up again in the right way, and now replacing this term here in terms of V. Then we end up with this equation, which is nothing but such an equation here, where we have a power, and here we have a compact linear operator acting on V, and this is which is symmetric also, and this is a perfect structure for the dual variational method. So we plug in the polychromatic ansatz and obtain a dual variational formulation for this function here, which depends now on x and t. So this is the difference here. So we have a functional, and what we check is it is well defined in C1. This operator here is compact. So once this is checked, you can apply the symmetric mountain pass theorem, and you're essentially done. Let me just mention briefly how the boundedness of K is checked, because this is the most challenging aspect here in this approach. So you have here the operator KV. It's nothing but this one, and then you use the Hausdorff-Young inequality, perform some estimates, and you come up with estimates of that kind here, where you have to estimate these operators. And now you need bounds for these operators here, namely bounds for these right inverses of the Helmholtz equation. Yeah, so you have to estimate their norm bounds, and under our assumption, we could show that this is actually a scaling argument, so there's not much to show. That this decay rate of these norms is given by this formula here, where alpha is this number. You can forget about the numbers; it's not so very important. But again, you can use some elementary computations to get at the end. And here you have to make sure that this sum here is finite. So you need that your alpha and your p match in such a way that this gives a finite series. Let me stress that here this is a sum only over the odd modes. So k is equal to 0 is excluded here. So you have to use that these operator norms decay sufficiently fast at infinity, and once you have this, you have the right mapping properties, and that's actually where our conditions on P and Q come from. Yeah? So we have to use that alpha is sufficiently large. So this number should be sufficiently large in terms of P, and this is the condition on P and Q that we encounter. Okay, so in such a way, when one can prove the boundedness, let me only mention that the compactness is easier under our assumptions at least, and so we end up with this functional here, which is well defined, which is C1. We can verify it has the mountain pass geometry. Given that this K is compact, one can prove that J satisfies the Palais-May condition, and you apply the symmetric mountain pass theorem and get the result. That's it. So the crucial thing here is to derive the functional using this polychromatic ansatz. Okay, I can now come rather to quickly to the end. So let me just mention a few generalizations. Instead of the Laplacian, we can take more general operators here, which can be elliptic, which in principle could be also different. And we only have to require that three abstract conditions hold, which are all satisfied in our setting. And the crucial ones, which gives the conditions on P and Q, is that one here. So we need a growth bound or a decay rate, say, for these norms. If we have a good decay rate, then everything is fine. So the better the decay rate, the better your mapping properties are, and the better your result is actually. Anyway, we can deal with such an equation, use these abstract sets of assumptions, and obtain the existence of an unbounded sequence of distributional breather solutions. And this can, for instance, be applied to the Klein-Gordon equation, fractional wave equations, biharmonic wave equations, and also perturbed wave equations. And for all these equations, we get breather solutions. And the open questions are, can we do this also for Q is equal to 1? So when we don't have a vanishing condition at infinity, the regularity and pointwise decay of our breathers is open. And the big question would be whether there's any idea for finding exponentially localized breathers in higher space dimension. And that's the end of my talk. Thank you very much for your attention, and obrigado pela sua atenção.